So far, we would be dealing with Ising-like situations, which means that the models we're considering were characterized by discrete symmetry. And the Ising model, in particular, one-dimensional Ising chain, is one of the examples of this kind. And we were able to solve it exactly, and we have found that the solution is in full, and of course, demonstrate the correctness of our intuitive suggestions and anticipations. We did obtain the correlation length, and we also were able to show how this correlation length follows from simple RG arguments. Now we turn to a completely different system, which is a two-dimensional model of planar spins. So if we imagine a magnet, a three-dimensional isotropic ferromagnet, classical ferromagnet, right? Even in case the spins are quantum, ferromagnetism as a phenomenon is much more classical than antiferromagnetism. Perhaps you know it. If you don't, then with Professor Kisilov you will learn. And now imagine that on top of this isotropic exchange interaction between the spins, there is an anisotropy. Basically, if you have a three-dimensional, the symmetry with respect to three-dimensional rotations, which means the original symmetry was SO3, then you can imagine that there is an anisotropy applied in the system, characterized by a certain direction. Say it's Z. This is not the Z space in real space. In real, is the coordinate space. This is a Z axis in the space of components, right, of the spins. And then you can imagine that this anisotropy can be twofold, actually. It can be the so-called easy axis anisotropy, which will bring you back to the Ising model. Easy axis means that the spins have preferred direction either along the anisotropy axis, either along or opposite. So this is the easy axis situation, this or that, nothing else. It depends on the sign anisotropy. If the sign anisotropy is different, then instead of easy axis anisotropy, you may have an easy plane anisotropy. That means that your spins can only change within a plane. They are two component spins. But otherwise, everything can be isotropic. This is precisely what is meant by planar spins. Planar spins are the objects, instead of the spins we can push outside the magnitude of the spin and then introduce a unit vector n. And this unit vector n basically has two components, n x and y, only two. And you can parameterize these components by an angle. And of course, the square of this unit vector is 1. It's a unit vector. The other thing is, where should I place the spins? That's another story. It's the dimension of the Euclidean space R. It's R2. And then in this space, I imagine that I have a two-dimensional lattice. And at each side of this lattice, at each side R of this lattice, I introduce this unit vector n at each side. But if I do that and say nothing, then there is nothing to discuss at all. So I have to put some interaction. Therefore, I introduce this interaction in the following way. I assume that there is a ferromagnetic kind of coupling between this unit vector field. So this S square coming out from the product, scalar to scalar product of two spins, can be absorbed in J. So what remains is just the scalar product of R and R prime. You add simply J is positive, which with a minus sign, that means that it's a ferromagnetic model. Spins are planar. And you can immediately say that at T equals 0, at 0 temperature, the minimal configuration is the one where all the spins look in the same direction. That's a typical ferromagnetism. But where is this spontaneous magnetization directed? Anywhere. Any direction is fine. The only thing is it has to be global, fixed for all the spins. Otherwise, you have full degeneracy. But since the dimension is 2, there can be no long-range order at any finite temperature. This is the Merwin-Wagner theorem, you know. Let me explain again why. Because the global symmetry of this model is O2. It's basically, apart from reflections, is basically planar rotations, the standard rotation you have learned from planimetry when you were in high school. Right? With respect to all these global transformations, this Hamiltonian remains invariant. It doesn't change. So this is the continuous symmetry. Since the symmetry is continuous and since the space is 2, space dimensionality is 2, Merwin-Wagner theorem tells us there can be no phase transition at any finite temperature because fluctuations destroy long-range order at any finite temperature. And we'll see how it comes about. We'll see. Now if we parameterize everything by the angles, then an equivalent form of this Hamiltonian is as a cosine theta of r minus theta r prime, and our rotational invariance shows up in the invariance of this Hamiltonian under global planar rotation. I can shift the angle theta r by an arbitrary amount omega, which has to be uniform, should not depend on the location, on the location in the real space. That's what global transformation means, right? So this is a clear invariance because this minus sign guarantees that this expression is just invariant under this. It's very, very much like what we have with translational invariance. We have a function which depends on two coordinates, r and n prime, and we know that this system is translational invariant, then we conclude that in fact it can only depend on the difference. Because every time you make a shift of the coordinate by a finite and global uniform vector, it cancels out at this difference. The same holds here. So the angular variable theta of r varies within this interval, which means that from the point of view of symmetry, from the point of view of exact definition, the space of degeneracy, which appears here, is compact. It represents a circle. Theta of r is a scalar quantity, but it is not a standard scalar quantity which takes any values on real axis. It's an angular variable which varies only within this interval, which means that the theory possesses invariance with respect to such shifts. This is 2 pi invariance, right? And by the way, this extra
extra terms may not be global, may be even local. Because every time you have 2 pi times the integer, it's a periodic property of any trigonometric function, cosine over sine. This is very important in the end of the day. So, that's very good. Now, why this model is interesting? First of all, perhaps I have to tell you that it was at the center of attention of excellent theorists across the globe in the 50s and the 60s and the 70s, that it was one of the most challenging, unsolved mysteries in statistical physics. I'll tell you what the mystery is about. Suppose you go to the low temperature limit. The temperature is much less than J. And you know that at any small but finite temperature, there is no longer a J. Which means that our first observation is an average at any point R, which does not depend on R, is there. No longer a J. No local multiplication. The system is disordered. Okay, what do we know about the disordered systems? About disordered systems, we know that such systems are basically fit the main postulates of statistical physics and can be thought as a superposition of different subsystems. Why? Because the correlational length is finite. This is what we assume in most cases now. Right? It turns out that if you calculate in this specific case the correlation function, it will give you not an exponential decay, but rather a power law decay. A power law decay at distances much greater than interatomic distance, which means it's a long distance asymptotics, with exponent which is not fixed, a fixed number, but which instead turns out to be a continuous function of the temperature. We will derive this result today. So, the fact number one, even though the system is disordered, the correlations follow power law. You know that power laws are only present when you are at criticality. Now, you know that if you compare, for instance, the situation with the one-dimensional Ising model, there too, at zero temperature, you are ordered, but as long as you deviate from temperature, if you switch on a finite temperature, you generate a finite correlation length in 1D Ising model, right? 1D Ising, which is proportional to this exponent, and which at low temperatures is exponentially large, but finite. Here, the correlation length is infinite. There is no decay exponential. There is no length scale. There was a question. This is a scale invariant. This is the demonstration of scale invariance, which holds even though you are not ordered. Any point at low temperatures, any value of this temperature means that the system is critical. Not at the point, but in the whole interval. So if you draw the time axis, temperature axis. Here, there's a zero when you have a long range order only at this specific point. At any other point, J is somewhere here. We are talking about
small t limit. All this line is a line of critical points. Not a single point, but a line. A completely new situation, right? So the good question is how this comes about. Well, the second observation is that even though you are critical, the critical exponent is not universal as it was supposed to be. The theory of phase transition tells us that universality implies that once you are at criticality, the only thing which matters is space dimensionality and the symmetry. Space dimensionality is 2, fixed. Symmetry is SO2 or O2, fixed. So, this exponent is supposed to be fixed, but it is not. It continuously depends on the parameter, on the temperature. So, universality breaks down. One of our basic assumptions is ruined. This is a counterexample. When the standard idea of phase transition does not go through in certain cases, and in those certain cases, and this is one of those, have to be treated completely separate. But this is not the end of the story. If you look at this model, at this particular more carefully, these are just objects which couple to each other pairwise. And you're asking the same question, what is the coupled behavior of the correlation function, but at temperatures which are high? One of your colleagues, you, asked me that. It's last time when we were discussing the Azimuth. It looks like a high temperature expansion. Suppose just we do this high temperature expansion, assuming that the temperature is much higher than J, the opposite case. You will immediately arrive at the conclusion that the correlation function behaves exactly as it's supposed to do. The correlation length will behave as some exponent as distance, r minus r prime, divided by some sum. And you will be able to calculate this correlation. In other words, if I continue this and fix some characteristic value of J in the temperature range, which is T much greater than J, whereas this is T much less than J, the correlation length is finite. So we have two kinds of behaviors. The low temperature behavior, the correlation length everywhere is infinite. This is a critical point, critical states, plural, all of them. And here you have the region where the correlation length is finite, because in the end of the day, whatever is the interaction at the temperature prevails, only thermal fluctuations determine the picture. The spins are basically independent. They satisfy the standard statistical physics of independent spins, and then you switch all these correlations perturbatively and calculate step by step, and then you find out the correlation length is finite. So there should be a transition, therefore. Because you cannot have both. You cannot have a smooth transition from infinite correlation length to a finite correlation length. Somewhere in between, there should exist a transition point. And this transition point has three names. Two of them were awarded the Nobel Prize a couple of years ago. Kosterlitz and Powers. And this is Mr. Berezhinsky from the former Soviet Union, who unfortunately died being very young. Even before Kosterlitz and Powers, 1 year in advance, he was able to figure out what happens in the two-dimensional planar model. And then it turns out there are new phase transitions. This is not the phase transition we were discussing up to now. This is a completely different phase transition, and the origin and the mechanism of this phase transition has nothing to do with what we've been discussing so far. This phase transition has a deep topological origin. Because the reason why this new transition occurs is the existence of new topological defect, the so-called vortices of the field N, which appear in pairs, which can form either dipoles, which look as neutral objects from large distances, or they dissociate in this case, and their dissociation gives rise to an appearance of the final correlation. So this is the plan of our work for future. So far is we have to start from something. And what we will do immediately, right now, is forget about what happens at high temperatures. Let us concentrate on low temperatures, today at least. The temperature is much less than J. This is the condition, which means that we are touched very, very close to the zero temperature case, which means that all configurations which should resemble locally the ordered ferromagnetic state, which means that if in the ferromagnetic ground state we have all the speeds exactly upwards, then if we look at make a snapshot of our system at a finite temperature, we'll find out that the speeds may change their direction, but in a very, very smooth fashion. You see, if I take a sufficiently large but finite domain with large number of speeds, at low temperatures it will resemble a ferromagnetic state, because there will be a more or less preferred direction. And then this magnetization slowly varies in space, never undergoing jumps. It means that for nearest neighbors, if R and R prime are nearest neighbors, the difference between the two angles is small. The misorientation of neighboring speeds is extremely small. The angle between them is very, very small. The angle itself may not be small, it may be close to 2 pi or 2 pi minus something. The difference is small. I don't care where the magnetization looks at this point. I do care about what is the orientation of neighboring speed with respect to this one. And this misorientation is small. Since it's small, why not to expand this cosine? So it will be justified if you consider only smooth, slowly varying configurations. Let us assume that this is possible, and then what we will have out of this will be the following thing. Our H will give us a constant, which is nothing but the minimal energy state when all thetas are equal, and then plus J divided by 2, sum over R prime, theta R minus theta R prime squared. Correct? Yes. Plus higher order terms. Delta theta squared. Well, if the relative change of this theta is small, what you can do, well, this is the energy of the fully polarized states. It's n times j. It's clear with a minus sign, of course. And here what to do, exactly, you remember that the summation over nearest neighbors goes to 1/2 summation of all latest signs, summation over nearest neighbor vectors, j, and the j is here plus minus a of x, plus minus a of y. On a given site I have 4 nearest neighbors, to the right, to the left, up and down. So therefore here I have theta n minus theta n plus j,
and these values are very, very close. And since these are close, the quantity m, which is the lattice, the notation for the lattice side, can be replaced by a continuous coordinate, which means that we are passing to a continuum limit. And if we do so, we will end up with a coarse-grained field. You know what coarse graining is already. Coarse-grained field, theta of x, which is a continuous field. And here what we need to do is just to replace this difference by j times the gradient plus higher order terms, and then do all the summations with respect to g. I leave it to you. Maybe I will ask you during the exam or something like this. Be ready for that. The result is what you will obtain after all in this continuum limit will be your Hamiltonian, which will take the form E naught plus j divided by 2 d2x and gradient theta of x squared. Quite often, not simply quite often, but all the way, we will be actually not interested in the Hamiltonian, instead we will be interested in the Euclidean action, which is the Hamiltonian in units of the temperature, up to constant, which I'm not interested in at all. I will write down this as tradition to replace it by a number of k, parameter k is the ratio j divided by t, and the gradient theta squared. At this point we make a stop because we observe something illegal, so to speak. Do you see anything illegal in this construction? Does it come to you as something which is contradicting our original statements and assumptions? Compare this to this. What is illegal?
The global safety angle.
Global what?
Safety.
This is a typical Gaussian model. For a scalar field, theta of x, x is a coordinate, two-dimensional coordinate. We know everything about it. We will find out certain things specific to two dimensions, but before that, if you compare this field theory with this field theory, this is also a field theory, but it's a discrete field theory. Field theory, because the number of degrees of freedom is infinite. And for an infinite lattice, the number of lattice sites is infinite, so therefore theta of r transforms to a field which takes discrete values, which is defined at discrete points in real space. What about the values, suppose it's allowed to take? The original field was an angular field, was an angle. Its space was a circle. The scalar field, theta of x, varies on the whole real axis. No periodicity. Because it's only gradient matters. The original information about the fact that theta was an angular variable is completely disappears. So we have sacrificed one of the main features of the original model on a discrete lattice, periodicity, 2-pi periodicity. It does not exist anymore in this approximation, which does not devaluate this approximation, but gives us a warning. Be careful, not everything derived from here will be correct. At some point we will find out some difficulties. But let's keep this in mind, but let's find out what this theory is able to give us. It's a nice model. It's a Gaussian model. Gaussian means that all these path integrals can be done exact. This is what we understand. And the most of all, what we are interested in is the behavior of the correlation function, gamma of x minus x prime, which is the average of theta x prime. And for any quantity A, this averaging procedure means that you calculate a fraction when you integrate over all values of theta. This is your A, which in turn may be some function of this field. You have the section, which is already written here. And then you define the partition function, which is the denominator of the whole expression except for this one. This is the partition function, right? So don't be afraid. The dx is axis. The way you should perceive it, you can think of. You can again go back to some kind of discrete two-dimensional lattice if you wish, and define at each later side this p of theta, which varies from minus to plus infinity, and therefore this d of theta will be understood as the product of all r from 0 to infinity d theta r. This is the roughly what is meant by differentiating. Or otherwise you can expand theta of x in Fourier series and then perform summation over integration over all Fourier components of this field. There are many ways to do it. I just sketched only one. Very good. We have to calculate. This is what we are interested in. So, how to do these calculations? Here comes the main problem. If we know how to solve this problem, then we know how to deal with the Gaussian model. There is an exercise there for you. Suppose you have a probability P of x. X is a single real variable, which is proportional to minus 1/2 some alpha x squared. Alpha is positive. It's a typical Gaussian function. It's a Gaussian distribution. The probability of the quantity x is given by this Gaussian distribution. Suppose you want to average the following object, the exponent I, beta, and x. Averaging of this quantity means that you integrate from minus to plus infinity dx. This is your distribution function. Then you write down the function you want to average, and defined by normalization integral. Due to the fact that Px is a Gaussian distribution, altogether amounts to writing an exponential which has the following structure: minus 1/2 alpha x squared plus I beta x. It's a polynomial of the second order. And you can suitably change the variable in such a way that you eliminate this I beta x. And if you do so, you will prove a very important theorem, which is known under the name as Baker-Hausdorff formula. If x is a Gaussian variable, which means that if
the probability function for x is a Gaussian, then this average is equal to minus 1/2 beta squared x squared average. Averaging again goes with this probability distribution, which is elementary in this case because if we have x squared here, just blindly write down the answer. It's so trivial. What is non-trivial is that if I average the exponent, I can now think in terms of the exponent in the sense of Taylor expansion. You have term 1, beta x, beta squared x squared, and higher order terms. It turns out that everything can be balled up in such a way that at the end of the day I get an exponent, and the averaging gets directly into what is written there, the exponent of this like it's written. This is for simple integrals. Now here we have functional integrals, path integrals. Turns out the same procedure follows, just the same, and we'll derive it. Before we do it, let me, is it clear? This is one of the problems you are supposed to solve. You have to prove this. You have to prove this. For this simple example. What you will not be able to prove, this is exactly what we will discuss now, because we have to learn the tricks which so far you were not aware of. Let me make the following thing. Let me denote k square root of k times theta x. Let it be phi of x. Let me introduce a new field which differs from the original one by the square root of k. I want to do it because I would like to replace my action by Gaussian action in terms of the phi field. It gives me simply 1/2 d2x and radian phi squared. No coefficient in phi. Right. If I plug in that, then I will recover the original formula. Fine. Now what I would like to do is to ask the following question. I would like to introduce the following expression. In what follows, integral over x will denote integral d2x. To avoid this long form, I will simply write it down like this. J of x, phi of x. X is a two-dimensional coordinate. I don't write the vector, but you have to understand that it's a two-dimensional vector. Phi is the field. And J is a C-number function, a real function. It's called the source. It looks like a magnetic field which couples to magnetization, if you wish. The only unknown, a new, unexpected object is the imaginary eye, which stands here. But it's important. We would like to calculate this average. To calculate this average, we would have to, if we follow just all this, it will be the integral over define. Here we are. The exponent minus action, minus this action, minus 1/2 grad phi squared. Plus I into J phi and divide on this exponent. try to apply basically the same trick as in the previous simple example, which you are supposed to treat as an exercise for your homework.
So should there be the second part in the denominator?
Yes. So, yeah, of course. Yeah. Of course. Otherwise, it's trivial. Of course. Right. Yeah. So what I would like to do is just to change variables in this integral, and this can be done as follows. Let me consider this expression. Let me denote it in some way. F is defined as minus as the integral over x minus 1/2 grad phi squared plus I j phi. Right? With your permission, I will rewrite it in the following way. I will write it phi double square phi plus I j phi. Is it clear what I do? I integrate it by parts. Right? Because I have delta phi times delta phi, and I would like to give it as delta phi, delta square phi, with a minus sign, because one, and plus the free term due to boundary conditions, it goes up. Right. Now I make a substitution. The substitution goes as follows. I will replace this field by a new field which is shifted by some C number function. Now it doesn't matter whether I'll define this function lambda with I or not. Let me introduce this I here. This f will transform to integral over x, so we have 1/2 phi prime plus I lambda. Here I have lambda squared phi prime plus I lambda squared lambda, and plus ij phi prime plus I lambda. All right. So the first term is done. It's something which recovers the structure of the original integral, right? Now there are second terms. I divided by 2 lambda double squared phi prime. In here I have I divided by 2 lambda phi squared phi prime Laplacian of lambda. Here I have minus 1/2 I lambda Laplacian lambda plus ij phi prime, and this gives me minus j times lambda. All right. So this is the something which is expected to be seen, because I studied transforming the Gaussian model. The basic term, which is proportional to the Gaussian model, should be present there. Now, what is unpleasant? The unpleasant thing is this one. I want to eliminate terms linear in the field phi prime. Right? I have 2 such terms, 3 such terms. This, and this. But this is fine, but here I can do the following simply. I realize that I can integrate by parts twice. Once I will get delta lambda, nabla phi with the minus sign, and again I will reduce this to that with the same plus sign. So I will therefore remove this and write down this. Correct? And then I compare these two terms, and I want them to cancel each other. For these terms to cancel each other, the following equations, lambda of x should satisfy this equation. It's the standard Poisson equation. It should be perfectly aware how to deal with it. How shall we solve it? Very simple. We have to introduce the Green's function. If we introduce the Green's function, which satisfies the following equation, this is the standard equation, the Green's function for this operator, for the Laplacian. The Green's function of the Laplacian in 2 dimensions. Then the formal solution of the above equation can be written as the integral g x minus x prime, j x prime, and integration with respect to n prime. Indeed, if I act by the Laplacian acting on the x from the left, that will give me minus delta function. The delta function with the minus sign will filter out minus j at the point x. That's exactly what is written here. So this is a formal solution. Once I know the Green's function g, I know the value of lambda. For this value of lambda, I eliminate this, and I eliminate this. And of course I eliminate this. What is left here? Yeah. So what is written here is minus 1/2. Lambda is the integral. So I can, let's be more careful. Lambda of x, lambda square, lambda of x, and plus integral of x, jx, lambda of x. It will give me what? It will give me with the minus sign, by the way, with the minus sign. By the way, after I substitute this expression into this one, the result will look as a 1 minus 1/2 integral over x, integral over x prime, j of x, gx minus x prime, and jx prime. Check. If I use this equation here, I will get lambda x times j, and lambda x itself is the integral g times j. So therefore I will get this expression of the plus sign because of this minus. Here I have the minus sign. Minus 1 plus 1/2 gives me minus 1/2. Therefore the coefficient is correct. Conclusion. We have solved the problem. So the numerator, if I have this exponent, x, jx, phi of x, the numerator gives me just this construction. It gives me exponent minus 1/2 double integral x prime jx g x minus x prime g x prime times what? Times the integral, Gaussian integral in terms of phi prime, which does not contain any other fields. So it's the same as the numerator, because the numerator differs from the remaining multiplicative part in the numerator only by the fact that in one case the field is phi, in the other is phi prime.
It's a notation. Otherwise, they're simply cancelled. So this is the result. This is the result, which looks very much the same as you had before, but it is not quite clear what about this G in terms of this field phi. It has to be, they have to be related somehow, right? Now, let's look at this equation. We know that the delta function, the two-dimensional delta function, is the integral d to k divided 2 pi to the power x squared, exponent, that's it. With your permission, I will now expand the Green's function exactly in the same way. It will be exponent ikx times the Fourier transform of the Green's function. And then I will plug everything in. If I act by this Laplace operator on this exponent, I will get minus k squared times the same exponent, because it's the eigenvalue of this of the Laplace with this eigenfunction. Right? So the result is j of k and the dt is 1 over k squared. Right? Right. Now let's recall that our free Gaussian action has the form d2x gradient of phi squared. What is the Green's function? What is the two-point Green's function? Phi x prime. It can be written as the Fourier transform of this function. As the Fourier transform of this function, d to k divided by 2 pi to the power of 2. And the Fourier transform of this function is this. It's a Fourier of this one and this next one. And for the Gaussian model, we know that it's again 1 over k squared. Every time that you have a gradient square, you generate k squared. We have already had this construction in our previous lectures. So therefore, the correlation, two-point correlation functions of this field and the Green's function appearing here is the same object. Just the same object. In other words, what is written here now is everything here is clear. I should erase it because I need some space. What is written here is exponent minus 1/2 x prime j of x average jx prime. And now compare with the formula which I have erased. The same structure. Essentially the same structure. Here I'm averaging the exponent, and the result is an exponent of something which is averaged just there. Right? So with this information, we now are able to calculate our correlation function, the physical correlation function. Our physical correlation function, gamma, x minus x prime, was the average of the cosine theta of x minus theta x prime. It is the same as the real part of this exponent, this here. And it is the same as the real part of this exponent. j phi of x minus phi x prime, which according to this formula means that j is 1 over square root of k, which is the same as the square root of temperature divided by j. So I know this, and this is a very general formula. This is, by the way, the most important formula of the Gaussian model. If you know this formula, you know everything. You can prove the so-called Wick theorem in the diagrammatic techniques. You can open the green book of Jelesinski, and the derivations there are just, long and cumbersome, and here we have just this, and you can show that multipoint averages or correlation function, they decouple into product of pair correlation functions. And this is the essence of the Wick theorem. They can build up the diagrams. So, how to use this knowledge when calculating this one? The structure of this expression tells us that j of x should be chosen properly. Look at this, and how from this you have to obtain this one. Very simple. You write down j of x is g, and the sum of two delta functions, x minus x1 minus delta x minus x2. All right. When I substitute this, I will get an exponent I g phi x1 minus phi x2. Precisely what I have here. Different notations, x1 and here x1. So I simply have to use this representation for the source function j of x. And if I plug this into the final result, and this is the final result, I will get an answer. So what I need to do, I have to take this expression, put here, the same, put here. I have two integrals over x and x prime, which are elementary because I have delta functions everywhere. And then the functions will filter everything. And if you do that, you will find out that the result looks as exponent minus 1/2, of course, g squared, and now we will observe a certain doublings. You will find out, and you will check if everything is correct what I'm saying. Twice phi squared average minus twice phi x prime average. It is clear because I will have products x equal to x1 selection and x prime also equal to x1. This Green's function will occur at the same coinciding coordinates, so therefore it will give me phi squared. But there also can be cases when one is delta function from here and for x prime is delta function from here. That will give me gx1, gx1 minus x2 or x2 minus x1, but this in your notations give me just the same. Now at this point I simply introduce a new Green's function. It's called the regularized Green's function. X minus x prime. It is defined like this, is denoted like this in the literature. And is understood what is the standard original Green's function minus its value coinciding coordinates. Which coordinate doesn't matter because of the translation variance. Why it is done so automatically? The theory is smarter than the people who use it.
Yeah. Because this is divergent, and this is divergent, and only the difference is finite. This is because of divergences, short distance divergences. So, at the end of the day, everything is clear here. Do you need anything else? Because you everything else have in your lecture notes. I could erase it. I don't need it. So I now summarize our result, and our result goes as follows. The Green's function, the correlation function, x minus x prime, turns out to be given by g squared, and the regularized Green's function, let me write it down as it is. A regularized Green's function depending on the two coordinates. Now you remember that our Green's function is a function of the relative coordinate x. Now I don't have need to extract another one because I can use the single notation for this x. Or if you wish, I can use r by saying that r is the relative coordinate. Right? It should be given by this integral pi divided by square k squared here, and here I have to write down this one. This is how it looks like in the usual situation. But if I extract this from this expression, I will get a minus 1. Because this is the same Green's function, but for coinciding arguments. When r is equal to 0, this exponent disappears, and I have this expression. Maybe during the tutorial on Monday, I will teach you a few tricks. You can calculate this, even though it is not simple. You can look into tables of different integrals, certain different integrals, and different integrals, whatever. And you can try to do calculations by yourself. What I want to say is with this exponent alone, or with this number alone, each of the two integrals are divergent. For instance, if I calculate the first integral, if I calculate the integral d to k, 2 pi squared 1 over k squared, what do? Nothing depends on the angles, therefore 2 pi comes out from the integration and cancels 1 power. I will direct 1 to pi, integral from blindly from 0 to infinity, k dk over k squared, which is k, divided by k. Oh, horror. This is horror, because it's divergent both on the lower limit and on the upper limit. It's a logarithm. So what we need to do is to write down k maximum and k minimum. There is no problem with k maximum because we live on the lattice, and k maximum is 1 over lattice space in the angle. You always understand. Discreteness of the lattice makes your life simple in k space because there is an upper limit. Like a Brillouin zone, for instance, right? What happens with the minimal k? If I set at k equal to 0, that's no good. So therefore I have to think in terms of a finite size system. And therefore the minimal k will be 1 over L. 2 pi divided by L if you wish. In the end of the day, this will transform to 1 over 2 pi logarithm L divided by A.
data space. So, again, it's divergent everywhere. Let's see. You know, in higher section, my considerations wouldn't be taken seriously because they treat short distances and long distances on equal footing. They never discriminate between the infrared physics and ultraviolet physics. Equally important, right? So, okay, I will also always say that, okay, I'm a condensed matter physicist because this should be taken seriously. This not always is present in any physical system. It's a minimal distance between the atoms or the particles. But what about this? I'm calculating the correlation function, and then I calculate the phi square average. And then, in fact, this phi square average diverges, telling me that indeed there should be no long-range order at any finite temperature. That's the result of this divergence. The phi square average appears if you expand the average cosine of phi in the Fourier series, in the Taylor series, writing down something like this. This will stand for the long-range order value, because for the long-range order, you fix the value phi, say, equal to 0. And then you ask yourself, what is the role of fluctuations? The fluctuation is this one. And this fluctuation turns out to be divergent when L goes to infinity. Therefore, in the thermodynamic limit, you don't have any cosine of phi, no such an expansion at all. Your assumption about the existence of long-range order fails completely. But by the same token, okay, you do the same calculation with this exponent, do the previous integral. It is more fancy, more tricky, because angles are there. So you will face the appearance, you will discover the appearance of some special functions, Bessel functions. It's inevitable. But all in all, you will find out that this also is divergent. Divergency will look like, roughly speaking, a logarithm L divided by x.
Actually, so last time you asked us to calculate the, there was a, how does the correlation function of the one of the problem that you did. So it is basically calculating this.
Yes. No, it's a common thing. It's a two-dimensional physics. It's 1 over k squared. It's a Goldstone mode, if you wish. It's always the same. This integral is typical, specific to 2 dimensions, and has to do with. No, it does not be specific to 2 dimensions. The logarithmic divergence is specific to 2 dimensions. Yeah, it's about that, and if you do calculations more or less accurately, you will find out that at large distances, when R absolutely is much greater than it all, we note the regularized Green's function, or the correlation, 2-point correlation function of the Gaussian field, regularized of x of R, gives me minus 1 over 2 pi. And now I'm absolutely happy, because I have to have it. I'm a condensed matter physicist, but the upper limit only depends on the distance between the space. The length has disappeared. This nasty object like L has disappeared because it should not be present in any meaningful expression for the correlation function, because the correlation function, as any correlation function, has to be calculated in the thermodynamic limit. In the thermodynamic limit, L goes to infinity. So no divergences are allowed to be present, so to speak. If they are present, then my starting point is wrong. Now I'm quite happy, but I'm more than happy because I can see one astonishing fact. Namely, if I use what is written here, my original correlation function, x minus x prime, turns out to be minus g squared divided by 2 pi, and the logarithm x minus x prime by a naught, which gives me a naught divided by the distance to the power of g squared divided by 2 pi, which is t divided 2 pi j. So what we have derived right now is the algebraic decay of the 2-point correlation functions of the order parameter field. The order parameter field was n, you remember, cosine theta sine theta. You put x here, it's a two-dimensional coordinate. You take two such order parameters, built at different points, build out a scalar product, and calculate the corresponding cosine using the Gaussian approximation. And the Gaussian approximation, this approximation is valid at temperatures well below zero. By the way, we have seen that the two-dimensional Gaussian model is scale invariant. Remember, we had such an exercise when we were discussing scaling and normalization. So this is an example of a scale invariant action. The theory is scale invariant. It could have been anticipated once we write down something like this. We are scale invariant. This is why we have a power law decay, and that is correlation length doesn't enter at all, doesn't exist. It's infinite. So this proves that there is a low energy, low temperature phase. If I draw now a diagram, again, come back to this diagram, and draw this axis, and this is t equal to 0. Somewhere here is j, this is t, and this is the region I'm interested in, t much less than j. Each point within this segment of the line, of the t line, t axis, is critical. Each of them. But the value, but it does matter where you are, because the critical exponents depend on t. So you keep being critical all the way along this piece, this segment. The correlation length remains infinite. But the critical exponents change. They vary. Which means that universality is broken. That's precisely how this phase is called quasi-ordered phase, or algebraic phase sometimes. These exponents are non-universal. And actually, basically, this is all what you can tell. One thing you can check, it's a good exercise here to show, that if you calculate the following thing, imagine that you have applied a uniform magnetic field, and you have polarized your system, right? The uniform magnetic field will end up with a finite magnetization, will induce finite magnetization. It's because you have broken the rotational symmetry. Right? But the fact is that if you switch off this field, and the temperature is not zero, then the magnetization will disappear as well, because you are not exactly at zero temperature. That's the point. Nevertheless, there is an interesting thing that if you calculate the susceptibility, so you fix the direction of this external field and then you add a little bit of transverse field.
and you want to change the direction, then in the limit, when the leading field, the applied uniform field, goes to 0, the corresponding transverse susceptibility will diverge. In the whole phase, in the whole low temperature phase. This divergence of this susceptibility means that the fluctuations are overwhelming, very strong, critical actually. They are not have any radius for that. So please take all these problems which are indicated in the lecture course quite seriously. And read good people, read John Carldage, read who else? Well, Mossad. Many points. Now we will, the next time we will ask a simple question. Whether or not it is possible to avoid this restriction. So if you have a Gaussian model and built up the Euler-Lagrange equation, right? You try to minimize the action as usual, right? As you do. You will derive the Laplace equation. That's for sure. Right? You derive this Laplace equation, and then you ask a very simple question that you have a system with interior D and the boundary DD, that's mathematical notations, with the linear sides of L, right? Then you restrict consideration by only those trajectories or those configurations of theta which keep S, and S is your Euclidean action, linear theta squared. Finite. Why finite? Because this exponent is the measure in all this path integrals. It determines averages for any physical quantity. So if the contribution of some trajectory gives you an infinite S, it does not contribute at all, because the exponent of positive infinity gives you 0. So therefore, you only consider those configurations for which the action is finite. And it's now clear that if L goes to infinity, it is crucially, vitally important to have gradient of theta equals 0 along whole boundary. Because if you don't, then this gradient will be accumulated somewhere. And when you go to the limit when L goes to infinity, you will be in big trouble. The action will diverge. So if you now accurately look at the solution of this equation with this boundary condition, no gradient at the boundary, at the infinite boundary, then the only solution you will be left with is this. It's a uniform vacuum. It's a ferromagnetic state. I'm talking about the Euler-Lagrange equations. I'm talking about those configurations that minimize the action. That minimize the action. What we are doing has nothing to do with minimizing the action. What we have done so far has nothing to do with that. Because what we have done, we have taken into account exactly, at least in this ligament, within the Gaussian model, all fluctuations, not only mean field, but all of them. All of them. I'm talking about mean field picture. Mean field light picture tells me if I minimize the action, if I write down delta is equal to 0,
I have no grounds for that. I have no right to do that. But if I insist that I want just this and nothing else, I will end up with Laplace equation. And with the boundary condition, will leave me only a ferromagnetic vacuum. You can sit down and work out, please. Now, good question is, the good question is this uniform vacuum the only stable, steady configuration which provides minimum for the action? I'm not talking about the absolute minimum, I'm talking about just conditional minimum, local minimum, if you wish. What about such configuration? So, locally I have all the spins changing slowly. But if I look for a larger distance, I find out that the direction of the spin of the field makes one full circle. And at large distances, there is something special happening at the center. But if I'm far away from the center, if the radius are chosen as large, then the relative change of the magnetization will be small. This will get worse and worse if I start moving closer to the center. Because on the square radius, I have to imagine something like this, which should transform to a continuous configuration, right? And this is a plaquette. This is the elementary square of the square lattice. I go back to the lattice from the continuum. Which means I'm in trouble. It's a singular point. I cannot have it in the continuous theory. But in fact, the theory is much deeper than that. Because what I'm trying to do, I'm trying to recover the configuration in which theta now recalls that it's in fact an angular field rather than a scalar field. I'm trying to restore the 2 pi periodicity. And then I have a problem. And the good question is, can I get such configurations as a result of minimizing the action, but under new conditions? And these new conditions will be described more accurately during our next lecture. It's not very easy, but there is a nice topology around all this. These are vortices which are nicely classified according to the so-called homotopic group. And this can be attributed a certain number, the so-called topological number, or topological charge. And the story looks very much like electrostatics in 2 dimensions. There will be positive and negative topological charges, positively charged and negatively charged vortices. And all this will unfold into a new transition, the so-called Berezinski-Kosterlitz-Tauris transition. Okay, so far, so good. We are done.